We are all familiar with the displacement function for simple harmonic motion, which is x is equal to a sine omega t plus phi. And some of us might also be introduced to the differential equation that represents simple harmonic motion, right? But how do we actually come up with these equations and what are its derivations? Well, today we are here to discuss about that and know how these derivations actually come up from. Okay, so in order to come up with that, we suppose that a particle of a certain mass, let's say small m, is in simple harmonic motion based in a perfect or ideal system. Let's say, for example, it's a spring with minimal friction. Now, if you plot the displacement versus time graph for this, it kind of looks like this. See over here, the x-axis represents time and the y-axis represents displacement. So any particular point over here would be t1 comma x1. Now, if we represent this in a spring, it also kind of looks like this. Now, you see, let's say that a force of F is applied on an object which is in simple harmonic motion, and the object of mass m, or the particle of mass m, is connected over here. So you would say that the force which is restoring the object is pushing it in this direction, and we label this as F restoring force, right? And the restoring force is actually in the opposite direction of the displacement, which is this, right? So by intuition, we could say that F is directly proportional to the negative of x. Well, this can also be deduced by Hooke's law, but yeah. So F is directly proportional to the negative of x because the restoring force is in the opposite direction of displacement. Now then again, from Newton's second law, we could also write F is equal to ma. Now for the proportionality constant for F is directly proportional to the negative of f of x, we could say that F is equal to negative k of x, where k over here is our spring constant. Now if we combine equation 1 and equation 2 over here, we would end up with ma being equal to the negative of kx. Now you see over here, acceleration is basically the second derivative of the displacement function. So we could also write this down as now if we divide both sides by m, we end up with. Now when we discuss simple harmonic motion, SHM, we label this term k over m as the square of the angular frequency. So we could say that our given equation over here can be written down as, and this is the differential equation for simple harmonic motion. Now, the solution of this differential equation over here should be x is equal to a sine omega t plus phi. And this is what we deal with when we discuss simple harmonic motion, and we take for granted x is equal to a sine omega t plus phi to be the displacement function for any particle in simple harmonic motion. But how do we come up with that? Well, the mathematics behind it is going to be discussed today in this lecture. Now, when dealing with the solution, we use the integral method to come up with our required equation. Now, in the integral method, we say that we first take our equation, which is the second derivative of x plus omega squared x is equal to 0. And then what we do is we multiply both sides with dx dt. Now, using some simple algebra, we could write that this dx dt as the velocity, and then again the second derivative of the displacement function can be written down as the first derivative of the velocity function. And then we could further write the equation that is the terms that are after this as omega squared x dx dt. Now, if we multiply both sides with dt, we are basically left with this equation over here. Now what we do is we take the integral of both sides, and then we are left with, now we see over here, if we do the simple power rules and whatever that are required to integrate this function, we have that this is basically v squared over 2 plus omega squared x squared over 2 is equal to c, where c over here is the integration constant. Now, if we do some further algebra, we could write the other parts down as, now you see 2c over here is still a constant, so we can term this as c in and itself because it still is a constant. Alright, now you see this velocity v over here can again be written down as dx dt whole term squared plus omega squared x squared is being equal to c. Now, here's where the actual part of understanding comes into play. At the position being at the amplitude, we know that the entire velocity v is basically 0. Now, if that really is the case, we could write this down, which is equation 1. We could write equation 1 down as omega squared a squared is equal to c, and label this as equation 2. So now we have a term for our constant c, and if you plug equation 2 into 1, we would actually be getting an actual value for c. And we have that. Now, if we simplify this entire thing, we could write this down as this equation over here. Now, our objective is to find x is equal to a sine omega t as our actual solution. So we need to break this velocity down into something that represents, let's say, displacement, right? So we could write the velocity down as dx dt squared is equal to omega squared a squared minus x squared, right? Now, dx dt can also be written down as the entire square root of whatever there is at the left, right? So dx dt can also be written down as omega the square root of a squared minus x squared. Now, we could also, what we do is we isolate everything that is in terms of x at one side and everything at the right. So what we do is we keep the dx over here to the left, and we divide both sides by the square root of a squared minus x squared, and we have that this is omega dt. Now, if we take the integral of this, we have that the integral of dx over the square root of a squared minus x squared is equal to the integral itself. Now, if you're familiar with the integrals of inverse trigonometric functions, this turns out to be sine inverse of x over a. Some people will also write this down as arc sine of x over a. It's still the same thing. Arc sine of x over a is the same as sine inverse. This can be written down as omega t plus phi, where this is the integration constant, and this integration constant can also be termed as the phase constant for simple harmonic motion. Phase constant. Okay, now we take the sine function in both sides. Taking the sine function in both sides, we have that x over a is sine omega t plus phi. And of course, we take the sine function of both sides. Now, if you multiply both sides with a, which is the amplitude, here you go. You have x is equal to a sine omega t plus phi. And this is how you derive the displacement function for a particle exhibiting simple harmonic motion. See, this is quite interesting because we started off with a particle of a certain mass and a spring, which has a certain spring constant, but we end up with such an equation that is independent of either the mass and the spring constant itself. Well, I find it interesting. I don't know about you guys. Anyways, that's all for today.